Okay, this video is a short example of a solution approach to question 3 of exercises 1 in the EGH 303 Aerodnamics lecture notes, which is in section 3.9 of your course notes. Question 1 we've been through in class. Question 2 I set you for homework along with section 3. Question 2 should be fairly straightforward. You just essentially plugging some numbers for free stream velocity and kinematic viscosity into the Blasius solution results, which are available on the formula sheet or available in your lecture notes, to work out boundary layer thickness and what else have you got to find? The transition point from laminar to turbulent flow. Question 3 is a little bit more involved, so this is a solution, a work solution for that question. So let's read through the question to give us a feel for this. Now, what I normally do if I've got a complicated question like this is that as I'm reading through, I would sketch a little diagram, just and make a note on that diagram of some of the things that are coming up in the question so that you don't miss them. So we've got an expanding channel in a quasi 2D flow. It's a two-dimensional diffuser. So this might be the kind of flow feel, for example, you might get at the rear underside of a Formula 1 car, where you've got a diffuser to transition the flow from the accelerated flow that's been passing underneath the car back to the free stream. In this case, the diffuser is of length L. It's installed downstream of a blower, which is pushing the air in at this end here with speed u0, and the blower produces a uniform flow of fluid with velocity u0 in the x direction of an xy Cartesian coordinate system. The density and viscosity of the fluid in the diffuser are both constant, equal to rho infinity and mu infinity respectively. So this is an incompressible flow, and we're assuming constant viscosity. The horizontal wall of the diffuser coincides with the x-axis. So this is the x-axis here, where x equals 0 here, x equals L at the end of the diffuser. And at any point along this, the area of the diffuser is defined as a function of x, and the walls are straight. Using ideal fluid flow theory, the diffuser is designed to halve the fluid flow velocity over its length. So by the time you get to the end of the diffuser here, you've reduced the velocity down to u0 upon 2. Using ideal fluid flow theory, the diffuser, we said that, the quasi one-dimensional approximation is adopted, and the fluid velocity vector is assumed to be of the form just u of x. So what we're saying there is we're assuming, even though there's going to be some small vertical component in the velocity field, because the flow is expanding, we're going to ignore that component because it's going to be so small relative to the velocity component in the x direction. So our velocity field just reduces to u, a function of x, so a single value as you move through that in ideal conditions where we're ignoring viscosity. So the first thing to do is show that the area function, so the area as a function of x of this diffuser is that's pretty straightforward. And then determine v of x, so the velocity in this ideal flow as a function of x. The pressure, P, in the ideal fluid flow is equal to P0 at x equals 0, so derive an expression for P of x using the Bernoulli equation. And then we move on to the stuff that's of interest to us in this section, which is boundary layer theory. Boundary layer theory is used to analyse the effect of viscosity on the flow in the diffuser. The velocity of the flow outside the boundary layer on the horizontal wall is assumed to be equal to u, and the pressure in this boundary layer is denoted by curly p. So curly p is referring to the pressure within the boundary layer. What are the values of dp by dx and dp by dy in the boundary layer on the horizontal wall? Assuming that the boundary layer on the horizontal wall is laminar. Of course, remember, Thwaites' method applies only to laminar boundary layers. Show that according to Thwaites, the momentum thickness, which is one of the variables that appears in Thwaites' equation, is given by this form here. And then show that the boundary layer is likely to separate. We'll move on to that at the end. So I've sketched out already a quick a little explanation of what's going on here. So this is just a summary of the details in that in the question already. Let's add in a little bit more information that we now know from reading the question. So we know that out here in the free stream, the viscosity is mu infinity, the density is P infinity, the pressure here is P naught, and we know that initially we're going to consider this as being ideal flow with no viscous effects, incompressible, and then we'll think about the implications of the presence of the boundary layer. So there's going to be some boundary layer which I'm exaggerating in size here with a velocity profile that looks something like this, and inside this boundary layer we're asked to work out what d curly p, so my curly p's represent the pressure inside the boundary layer, and d curly p by dy, where the y direction is this direction. So the first thing that it seems sensible to apply to this is conservation of mass. So, or the continuity equation. So let's state that's the principle that we're using here. Conservation of mass across this diffuser tells us that rho infinity A, let's call this is A naught here, A naught times U naught must be equal to the density at the exit, which is the same, rho infinity times the area at the exit. So we'll call that A at x equals L times U naught over 2. So our rho infinities cancel, our U naughts cancel, and this simply tells us that A at x equals L is 2 times A naught, perhaps a result we could have just made by observation. We can now state that given the walls are straight, this implies that the area, if it's varying linearly between A naught and 2A naught, must take on this form. A naught 1, it's increasing, plus x over L, just by observation. So when x is 0, the area is A naught. When x is equal to L, the area is 2A naught, which is what we need at this point here. So the next thing we're asked to do is work out v as the function of x. So let's apply conservation of mass again, but between the entry to the diffuser and a random position, or a general position x along the diffuser. So conservation of mass again tells us that rho infinity A naught U naught is equal to rho infinity A is a function of x, U of x. Of course this cancels. It was v, wasn't it? This should be a v here, to stick with the notation used in the question. So v of x is going to be equal to A naught U naught over A naught 1 plus x upon L, which equals the A naughts cancel, U naught over 1 plus x upon L. Now I know later on in the question we're going to need to differentiate this, so we may as well do that now. To help us do that, it's probably easiest to write it in this form, 1 plus x over L to the minus 1, which implies that dv by dx is equal to minus U naught 1 plus x over L to the minus 2 times 1 over L, which equals minus U naught over L 1 plus x over L squared. Okay, so we're now interested in the pressure distribution through this diffuser. Again, still in ideal flow, and to look at variations in pressure. An ideal flow, Bernoulli's equation is the way to go. which of course is effectively a statement of conservation of energy. Bernoulli's equation tells us that the pressure at any point x over rho infinity plus a half v squared, or p plus a half rho v squared, is a constant, so it must be equal to the value at the start of the diffuser, which is p naught over rho infinity plus a half u naught squared. So we can rearrange that to get our expression for p, substituting in for v, which we now know from up here. But we're also asked to work out what dp by dx is. So we may as well do that now. So let's differentiate with respect to x, and we can get 1 over rho infinity dp by dx plus v of x dv by dx done that right? Yeah, just checking I've done that right, is equal to 0. So dp by dx is equal to, I'm going to substitute in for v of x, which is u naught over 1 plus x over L, dv by dx, which is minus, but I'm taking all of this onto the right hand side, so that will cancel the minus sign, so we're going to put times u naught over L 1 plus x over L squared, and I'm going to bring this rho infinity up, so we get a rho infinity here. So let's do a little bit of rearranging. dp by dx, this is in the flow, is rho infinity over L times u naught squared 1 over 1 plus x upon L cubed. And of course this thing, for all values of x between 0 and L, is going to be positive, so we can point out here that this is an adverse pressure gradient. The pressure is increasing as you move along this diffuser, which means that there's at least the risk that this boundary layer, that when we start studying it, is going to separate because we've got this adverse pressure gradient present. So let's start thinking about what's going on inside the boundary layer. Now in the boundary layer, we can make the assumption that v, the y component of the velocity field, is much, much smaller than 1. It's a very small value compared to u, the x component, which in turn implies that d curly p, this is the pressure within the boundary layer, by dy is effectively 0. Now if dp by dy is 0, and we know dp by dx at the upper limit, or the top of the boundary layer in this case, is dp by dx, and the ideal flow is this, then that means that therefore the pressure within the boundary layer, curly p by dx, must be the same as it is in the ideal flow outside it. So dp by dx must be equal to rho infinity u naught squared over L 1 over 1 plus x upon L cubed. So the next part of this question was to study now what's going on inside the boundary layer and look at, see if we can find an expression for theta, the momentum thickness of the boundary layer. So we'll start, we're asked to use Thwaites' method, and we always start with Thwaites' equation in Thwaites' method, which is given to you on the formula sheet, and it's this funny formula that we did derive in the lectures, but we can just write down in a situation like this where we're solving a problem, is d by d, so rho infinity over mu infinity multiplied by the derivative in the streamwise direction d by dx of v to the power 6 theta, the momentum thickness, to the power 2 is equal to 0.45 v to the 5. We can substitute what we know into this expression, so we can do rho infinity, u infinity, d by dx of, now we know what v is, this is going to be u naught to the power 6, 1 plus x upon L to the power minus 6 theta squared is equal to 0.45 u naught to the 5, 1 plus x upon L to the power 5. We can integrate this with respect to x to get rho infinity over mu infinity u naught 1 plus x over L to the minus 6 theta squared equals, when we integrate this, we're going to get 0.45 u naught to the power 5, 1 plus x over L to the power 6 over 6 times 1 over L plus an integrating constant. Nope, that's not right. So this should have been, why isn't that right? That's not right, because there should have been a minus 5 up here, which would make this a minus 4 here, which makes this a minus 4 down here. Apologies. And the job now is to work out what this integrating constant is. And the usual condition that we can apply to work out this integrating constant is to say when x equals 0, in this case at the start of the diffuser, theta, the boundary layer thickness, is 0. Theta is 0, the left hand side of this equation is 0. When x is 0, we get minus 0.45 over 4 u naught to the power 5 L. Is that right? Yeah, x is 0 plus c. So c is equal to 0.45 over 4, which is 0.1125, 0.1125 u naught to the power 5 times L. Let's call this equation star and say substituting for c in equation star gives us that, let's rewrite this as 1 over nu, the kinematic viscosity, nu infinity u naught 1 plus x over L to the minus 6 theta squared equals minus 0.1125 u naught to the power 5 times L over 1 plus x upon L to the power 4 plus 0.1125 u naught to the power 5 L. Rearranging that, gives us, we'll factor out the 0.1125, we'll bring the nu infinity up from the other side, L over, of course, so I've lost it to the power 6 here. So that is going to disappear. Cancel with that 6. So we end up with a u naught on the bottom here. And then on this side we have 1 plus x over L to the 6. checking what we're aiming towards here, make sure we're getting the right thing we are. So it's 1 plus exponential to the 6, factorising out 1 minus 1 over 1 plus exponential to the 4. I think that is the result we were looking for. Let's just check back to here, and yeah, that's what we were looking for. So the final part of the question was to show that the boundary layer on the horizontal wall is likely to separate for some value of x upon L, and it tells us what range to look in. Now remember, separation occurs when the shear force tends to 0, when this S parameter, which is part of the Thwaites method, is 0, and we were able to show that the Thwaites parameter was 0 when lambda is equal to some value which was minus 0.08, I believe. So I'll just show you what we do next in this question for you to finish off, because it's just plugging numbers into equations. So to finish this off and to show that the flow separates between x upon L equals 0.1 and 0.2, we can just consider the case for x over L equals 0.1. We work out theta squared by plugging plugging x upon L equals 0.1 into this. So we would get, in this case, 0.1125 nu infinity L over u naught. So we get 1.1 to the 6 times 1 minus 1 over 1.1 to the 4, and we get a value out obviously in terms of nu L and u naught, which we could then plug into the expression for gamma, for lambda, sorry. Remembering that capital lambda, this parameter that appears in the method, is rho infinity theta squared over mu infinity dv by dx. So this is equal to rho infinity over mu infinity theta squared dv by dx. Just check I've got that right. Rho infinity theta squared over mu dv by dx. Yeah, so we know what we'll find is that the rho infinity and mu infinity will cancel with these things. When we plug in the expression we get here for theta squared, we know what dv by dx is in terms of x upon L, and we'll get an expression out here. And then if you do the same for x over L equals 0.2, so in this case theta squared would be 0.1125 nu infinity L over u naught 1.2 to the 6 times 1 minus 1 over 1.2 to the 6, and we get a value out for theta squared. Work out the value of capital lambda in the same way, and you will find that these two lambda values sit either side of this magic value for lambda, which gives us an S value of 0, so they'll sit either side of this minus 0.0842. Again, all of the details of what these parameters are, what value of lambda you need for flow separation to occur, will all be on the formula sheet that you get in the exam. So I hope that gives you enough guidance to get you through question 3. If you're still having any problems, just get in touch with me.